We're using a thermocouple to measure temperature. A thermocouple consists of two wires of different types of metal joined at their ends. When you change the temperature of the junction between the wires, a voltage difference is created between the wires. We have what's called a type K thermocouple, which typically provides a sensitivity between temperature and voltage of about 41 microvolts per degree centigrade. The sensitivity of the thermocouple itself isn't actually high enough for our application. We have a design requirement for our temperature measurement system that the rate of change of voltage of the output with respect to temperature needs to be 5 millivolts per degree centigrade. A design requirement simply defines how our system must operate. It's set by whomever is using our system. We don't really need to know where it's coming from or why, we just need to create a system to satisfy it. In order to meet the design requirement, we'll add an amplifier to the thermocouple output. The amplifier will have a gain of K. We need to determine the value of K that gives the required overall sensitivity. Now let's do the math and find K. This block represents the thermocouple. Its input is temperature, which I'll denote as T. The thermocouple output is here. It's a voltage that I'll call Y. The equation relating Y and T is Y is equal to 41 microvolts per degree centigrade, which is 41 times 10 to the minus 6th volts per degree centigrade times the temperature. This is the equation of a straight line with slope m equal to 41 times 10 to the minus 6th and a y-intercept b equal to 0. The sensitivity of the thermocouple is the same as the slope of the line describing the relationship between the output and the input. I'll call this equation 1. The amplifier input is Y, and its output is a voltage that I'll call V. The equation governing their relationship is V is equal to K, the gain of the amplifier, times Y. This is again an equation of a straight line with a slope of K and a y-intercept of 0. I'll call this equation 2. We need the sensitivity or the slope between the voltage V and the temperature T to be 5 millivolts per degree centigrade per our design requirement. The governing equation then between the output voltage and temperature should be V is equal to 0.005 volts, which is 5 millivolts per degree centigrade, times the temperature T. This V is the same as this V. We can write this V in terms of equations 1 and 2 by substituting equation 1 into equation 2 here. V is equal to K times 41 times 10 to the minus 6 volts per degree centigrade times T. 0.005 volts per degree centigrade times T is equal to K times 41 times 10 to the minus 6 volts per degree centigrade times T. Equating these two terms, the T will cancel out. I can solve for K. So K is equal to 0.005 volts per degree centigrade divided by 41 times 10 to the minus 6 volts per degree centigrade. Doing that arithmetic, K turns out to be about 122. Units of volts cancel with volts, degrees centigrade cancel with degrees centigrade, so K actually has no units. It's typical, however, to give K units of volts per volt to indicate that the input to the amplifier is a voltage and the output is also a voltage. So there's the value of gain that gives us our sensitivity of 5 millivolts per degree centigrade.